So what I want to do for this video is actually start looking at carbon NMR spectra. And then we're going to talk about the second important skill that you need. Again, this will apply it'll apply to carbon NMR as well as proton NMR. But here's kind of what the typical carbon NMR looks like. Maybe not the number of peaks, but I would just want to highlight some features here. On the x-axis is going to be where the signal appears. And for carbon NMR, this runs from 0 to about 200, maybe sometimes um, a little bit more. But I'll talk about where the signal appears on the next page. But I want to highlight here, this is a very unremarkable NMR of benzene. And notice there's just one signal. And why is there one signal? Well, because all of the carbons of benzene are the same. Same chemical environment, so they're going to have the same, uh, just one peak, same signal. So let's talk about where a signal appears. And this is something we call chemical shift. And so the chemical shift is basic, as I said, is where the signal appears. And the kind of guideline that was established long ago for NMR was that everything would be based off of TMS. TMS is known as um, tetramethylsilane. So this is TMS. And they basically said for carbon NMR, wherever the carbons of TMS show up, that's automatically 0. And for proton NMR, wherever the hydrogen showed up, that would be 0. And then everything else would be judged based off of that. In fact, in the old days, they'd have to like put in a drop of TMS just to set their machines to the proper 0 mark. Nowadays, we don't have to do that anymore, but this is kind of like what the standard was, and that everything was based off of that 0 mark. And so for carbon NMR, the chemical shift will change as the environment around each carbon atom changes. And as I said, the scale usually runs from 0 on the right of the x-axis to 250 on the left axis. And where that signal appears is dependent upon this concept called shielding. If something is in a very electron dense environment, or we say it's more shielded, it's going to be farther upfield or to the right. This is a very important term I want you to know as far as location. When I say upfield, that means it's more to the right. It'll have smaller values. If the carbon is in an electron poor environment, or we say it's de-shielded, then it's going to be further downfield or to the left. It'll have a higher value on the chemical shift line. And here's the best way I can explain shielding. It sounds very like, sci-fi Marvel like, but let's compare this carbon to this carbon. I just want you to focus on the explicitly drawn carbons there. Now, which carbon do you think is going to have more electrons around it? This carbon over here is more shielded because it's not really involved in a highly or bonded to a highly electronegative atom, or there isn't a lot of electronegative stuff around it. But if we look at this carbon over here, it's involved in a very polar bond because that chlorine's a lot more electronegative. And so this carbon here is de-shielded because the electrons that were around it are now moving towards the chlorine. And that de-shielding causes that signal to be farther downfield. And so something like this might show up at around like, say, 20 ppm. But something with like a chlorine attached, maybe somewhere between 40 to 60 ppm. So when an atom, whether it's carbon or hydrogen, is deshielded, it's going to appear farther downfield. So the simplest way to explain this is the more stuff there is. I know that word stuff is a very technical term, but if you have things with atoms or lone pairs, highly electronegative atoms that are close to a carbon atom, the more downfield the signal is going to occur. So let's take a look at some of the relative chemical shift values. And I want to highlight here, these are approximate. Okay, because these are going to change a little bit depending on the compound the carbon is found in. But what I want to do is break up this table to a more manageable like group in the groupings. Okay, so from about 0 to 50, these are just usually sp3 hybridized carbons with no electronegative atoms attached. And again, this is approximate. This is most of the time. Yes, there are exceptions. They're very rare and few and far between. But then as we get into 50 to 100, these are going to be sp3 carbons with electronegative atoms attached. Again, this is a very general kind of thing. You notice that there are some overlap, and that's just things we'll take on a case-by-case basis. And you might be looking at this and saying, well, how am I supposed to know if I have a carbon with a halogen or a carbon with a nitrogen or a carbon with an oxygen? They all overlap. Well, how could you tell the difference? Maybe if we had an IR, IR would tell us if we got a nitrogen or if we had an oxygen. The molecular formula might tell us if we have those things. So you'll have a lot more information to deal with these kind of ambiguities and to deal with these overlaps. The other thing that you will find in this region are sp hybridized carbons. It's kind of in a weird spot. If you look at the trend, the trend suggests it should be sp3 on the low end, sp2 on the higher end, and then sp should be farthest. I don't have the time to kind of go into why sp hybridized carbons appear in this weird area. It's just something you need to know. And then past 100, usually from about 100 to about 150, are carbon-carbon double bonds. Again, this is a weird little exception here with a carbon-nitrogen triple bond. And then from 150 on are carbon-oxygen double bonds. So anything bonded, any carbonyl is going to be over there. And like you said, or like you're probably thinking, like, how do I deal with all this overlap? Well, you'll have more information given to know the difference between an amide or an ester or a carboxylic acid. Aldehydes and ketones do tend to be a lot the highest of the chemical shift values. So that might be a little something to remember. But I will kind of preface this and say I'm not going to give you this table on your exam. You will need to know the approximate locations for these chemical shift values. All right, so let's look at a few examples and we'll stop for this video. So let's take a look here at toluene. I'm going to draw the structure of it. We're going to match these carbons to the signals we see here. And I want to do something else here first. I want to introduce a kind of spectrum interpretation tip. Let's say you're not given the structure. So I'm going to take this away for a little bit. What's an important tool for interpreting NMR? Number one, look at the formula. Notice the formula here is just carbon and hydrogen. So if I ask you to draw the structure of this compound, you better not put an oxygen, or you better not put a sulfur or a halogen, because the formula tells me I don't have any of those things. I just have carbon and hydrogen. Number two, you're going to do a quick calculation called IHD, or Index of Hydrogen Deficiency. That's just basically a fancy term for how unsaturated is this compound. All right, so here's how you're going to find IHD. And this is something you're going to need to know this formula. It's the number of hydrogens if the compound were saturated. Minus the number of hydrogens in the formula. And you're going to divide all that by 2. So let's do this for toluene here. Toluene has 7 carbons in it. So if it were fully saturated, it should have 2n plus 2, or 2 times 7 plus 2 hydrogens in it. So it should have 16. But the formula says there's only 8. So I divide that by 2, and that comes out to a value of 4. Now, what does this number tell you? Every value of one IHD either represents a pi bond or a ring. So we could spend all day kind of like outlining the possible combinations for a value of 4. Well, maybe you have 4 pi bonds, or maybe you have a double bond, that's 2, and then 2 pi bonds, or 2 double bonds. Maybe you have a ring and 3 pi bonds. Like there's a bunch of different combinations for this. I'm going to give you a little hint here. Most of the time when you see a value of 4 or more, a value of 4 means benzene. Again, that's not like 100% certainty, but for most of the problems you're going to see, that's a value of 4 because it has 3 pi bonds and 1 ring. That equals 4. So if your IHD is high, like it's got 4, 5, 6, 8, start looking at benzene as being part of your structure. I'm going to do a lot more of these later, but I just wanted to introduce this concept of IHD. I'm going to modify this formula as we do a few more examples, but we'll get to that. So here's the actual structure of toluene. And let's just label the unique hydrogens. I'm sorry, unique carbons. So we got A there. And then we got B here, C, and D. So I'd expect to see 5 signals, even though I have 7 carbons. So this kind of lends to the fact that there is some symmetry there. And let's just label these on, actually, I forgot this one right there, E, sorry. Let's label these on our NMR. So I'm going to start with the CH3 there. That's an sp3 carbon. So I'd expect it to be in the sp3 region, which is like 0 to 50. So there's A. Now, how do I do these other ones here? I have 4 more signals, and notice they're here in my carbon-carbon double bond region. So I know these are all the ones that are involved in the benzene ring. So how do I figure this out? Well, the one with the highest chemical shift is going to have the most stuff on it, which is going to be E here. And then the farther away we get from all of that, like that methyl group, we're going to have B and C. Notice they're kind of really close together in chemical shift. And then we got D is the farthest away from all of that stuff. All right, let's look at another example. So here is para-ditert-butyl benzene. And let's do the IHD calculation just to get some practice with this. So the formula for this is C14H22. So how many hydrogens would this compound have if it were fully saturated? Well, 2n plus 2 means I should have 30 hydrogens. I only have 22. Now divide by 2, and that comes out to a value of 4. And again, most of the time when you see a value of 4 or more, you know that benzene is going to be present. So let's label all of our unique hydrogens. So let's start here, and I'll call that one A. That's going to be the same for all of these here. Now, do you see any others that could also be exactly the same as A? Let me give you a little hint here. Notice the top half looks exactly like the bottom half. That means all the signals on the top half are going to be exactly the same as all the signals on the bottom half. So all 6 of those are represented by A. And we could say the same thing for those two. And then for this one, we'd say the same there. And all 4 of these are exactly the same. So because of this symmetry, I have 14 carbons, yet only 4 signals. And so let's label these on our NMR. Okay, so I have a couple of sp3 types of sp3 carbons. I got A and B. So let's go over here. Which of those do you think will be A? Well, A is the farthest away from everything. And so it doesn't have as much stuff around it as B does. Notice B has 1, 2, 3, 4 carbons attached to it. It's got more stuff around it than A does. And so now let's go to our sp2 carbons here. So these are involved in benzene. Those are our carbon-carbon double bond region. Which one do you think is going to be further downfield? Which one will have more stuff on it, C or D? If you look at both of the C carbons, though they have tert-butyl groups on them, the D carbons don't. So C has more stuff on it than D does. All right, let's look at another example here. So here we have 1 pentyne. And just for practice, let's calculate the IHD. Okay, since it has 5 carbons, it should have 12 hydrogens. But it only has 8, and we divide by 2, and that comes out to a value of 2. Now, if we look at the actual structure of pentyne, it has 2 pi bonds, so that's where that value of 2 comes into play. Now, all of the carbons of pentyne are unique. I encourage you to kind of pause the video and go through that exercise. But let's label these. Notice C, D, and E, those are all sp3 carbons. So I expect them to be in the sp3 regions. And they're going to kind of go in order of how close they are, how much stuff there is around them. So notice E is the farthest away from everything. So it'll have the lowest chemical shift. And then D has a little bit more stuff to it. And then C is the closest of those carbons to the triple bond. And then now these two carbons are in that region, that kind of weird region for the carbon-carbon triple bond. But which one do you think will have the higher chemical shift, be farther downfield? It'll be the one that has more stuff around it, letter B. And then A, since it's farther away, doesn't have as much stuff around it as B does. All right, let's look at another example. So here's 3-bromo, 2-butanone, and here's the formula. So let's calculate the IHD. And this is gonna kind of show a couple of important adjustments we need to make to the IHD formula. If there is a halogen present, so a halogen means you add one hydrogen. If there's an oxygen present, you don't do anything. If there's a nitrogen present, for every nitrogen that's there, you're going to subtract one hydrogen. So here's how this works in the calculation. I should have 10 hydrogens if this were fully saturated. I only have 7, but because I have a bromine, I'm going to add 1 to that term. I don't do anything with oxygen. I don't care about it in this formula. And so 10 minus 8 divided by 2 is a value of 1. Now, had there been a nitrogen, I would have taken away 1 from that term. So every halogen there is, you add 1. For every nitrogen, you take away 1. All right, so let's label all the unique carbons. So there's no symmetry here, so every carbon is going to be unique. And now let's start labeling these. Now notice we have something here that we haven't seen before. There's a carbon-oxygen double bond. That should be kind of a big red flag that that's going to have a very high chemical shift. Carbonyls, remember, start at about like 160 and above. That's where our carbon-oxygen double bonds are going to show up. All right, now let's go to our sp3 hybridized section over here. Which carbon, A, C, or D, do you think will have the highest chemical shift? Well, C's got a bromine directly attached to it. That's a highly electronegative atom. That's going to have the higher chemical shift. Now, A and D, how do we know which is going to be which? Because A is next to a carbon with an oxygen, and D is next to a carbon with a bromine. And I want you to think about this in terms of electronegativity. Oxygen is more electronegative than bromine. And so that oxygen will have a higher effect on A than the bromine will have a higher effect on D in terms of de-shielding. So that's why A is going to be a little bit farther downfield. All right, let's look at one more, and then we will stop with these problems. One, two. Okay, so let's just do a quick IHD calculation. Again, this is going to come into play a lot more when we don't know what the structure is first. We have to figure it out. So This compound should have 14 hydrogens. It only has 12. I don't do anything for oxygen. I don't adjust the calculation. And so that's a value of 1. You look at the structure, that value of 1 is because of that pi bond. So for this compound, again, all of these carbons are unique. I encourage you to pause the video, work that out on your own. And so let's just start. Where would we put letter A? Well, A is an sp3 carbon, but it's got an oxygen attached to it. Really highly electronegative atom. So that's going to be in our sp3 carbon region, but have the highest chemical shift. And then where would I put B? Well, B's closer to the oxygen. C and D are going to show up in our double bond region. I'm going to ignore those for a second. And then E would be next, and then F would have the lowest chemical shift. Just kind of going down the line there. Now, if I'm going to go to my carbon-carbon double bond region, which do you think should have the higher chemical shift, C or D? Well, C has got 2 carbons and an oxygen over here. D's only got 2 carbons. So just by using the stuff rule, C should have a higher chemical shift than D. You can get a little bit more technical by saying, well, C is a little bit closer to that electronegative atom than D is. So which is why it will have a higher chemical shift.